Hello and good evening. Chijoke here. We are going to work with just a very simple explanation on fraud detection. So we're working with a fintech data set. So it's going to be a credit card fraud detection. So we want to see how we can build a model that will be able to predict whether a transaction is fraudulent or not. And most times the transactions which we have are a lot of the genuine transactions and very few of the fraudulent transactions. So most times the data sets of fraud detection problem is always imbalanced. But we're going to come to the area of what kind of technique we're going to make use of in working with that kind of data sets. So we are going to work on a Kaggle competition for a credit card fraud detection. So we're going to look at this competition. It's a very old competition, but it's going to give a little explanation. It's going to allow us to have a broad yet simple view of what credit card fraud detection problem is and how to be able to tackle it. So, like it was explained in the context that it is very necessary for fintech companies or credit card companies to be able to recognize transactions which are fraudulent from the ones that are genuine, so that they cannot charge for items to the customers who made genuine transactions for the things that they did not purchase. So this data set is we have, like I said, there are 492 fraudulent transactions where we have over 284,000 genuine transactions. So it's highly imbalanced. And these are like the features of the data sets V1 to V28. And then we also have the feature of the time and the amount, and then the targets. The target is for the class column, which has whether a transaction is labeled genuine, which is in this case is 0, or fraudulent, which in this case is 1. So we're going to just run through it. So this is the Jupyter notebook. So it's a small data set, so you can actually run it locally instead of running maybe in Google Colab or using an expensive platform. So the data set is here. Use this module to be able to find out the data set. So this is the data set, the credit card CSV file. So you are importing our modules. We're going to use pandas, we're going to use NumPy, Globe, and the matplotlib, and then this is the machine learning model we're going to make use of. So I've already worked on this data set, but I'm just going to be to explain on the code base of the data set. So here now, this is so we want to take the CSV file and put it into a format that can be used in Jupyter Notebook. So we are reading the CSV file now. So this is the CSV file, the credit card. So we are going to make a quick check of the columns. Like I explained before, you have the V1 to V28 columns developed from the PCA, principal component analysis, and then the time column, the amount column, and then the class column. I suppose this time column and amount column, we are still going to work on it because it is somehow different from this general one, but we are going to come to it. So since the information we need about whether the data set is balanced or imbalanced is coming from the targets, we're going to have a quick check on that particular column, the target column, to see how imbalanced or how balanced our data set is. So we're going to look through that particular column to get that information. So it's the column, the class column in our data set. So this is the function in pandas that does the counting of the columns, classifying them to the categories in which they have. I think it's numerical in this case because it's zeros and ones. Then it's going to sort it out. We plot it out using matplotlib, so to get the information that we need. So this is it. So this is the genuine transactions and then the fraudulent. So it is a very highly imbalanced data set. It's very highly imbalanced, and we are not going to work with it in this manner. We are going to see how we can either oversample it or downsample it, or use other techniques like the smooth technique. So, but the technique we're going to make use of in working with the dataset is the undersampling, and I think it was explained somewhere here. Working on imbalanced dataset, so downsampling. So it is a means of like. So we have the majority class, which is the genuine transactions, and we have the minority class, which is the fraudulent transactions. So it's in this context, it's about training the model on a very disproportionately low subset of the majority class, which in this case is the genuine transaction. So we are going to bring it down to a certain level of the fraudulent transaction. So we have a case of not just 284K genuine transactions and then 492, but 492 of fraudulent and also 492 rows of the genuine transaction. So it's in the case of 50-50 proportion. So you can have a good information on how the dataset is, and it will help us in good prediction of the dataset. So if you want to see like in a percent page, so it's always good to have information on what you're working on, a very detailed information. So you have seen it's imbalance, but to what extent or what percentage do we have of the genuine transactions and the fraudulent transactions? So we have the normal transactions, we have the fraudulent transactions. So we just run it. So we have around 99.83% of the normal transactions and 0.17, which portrays the first idea we are talking about, that we're not going to work with it in this way. If you ever try to do it this way and use the metric of accuracy now, it will give us accuracy of over 90%, even up to 99%, but it's actually false because it is not seeing the fraudulent transactions. It sees majorly the normal transactions and it mistakes it as the fact that the transaction is doing well. So even in the metric we're going to make use of, we're not going to use of the metric of accuracy. We're going to use the metric of ROC, area under curve. And I think that was what was mentioned in the competition, the metric we're going to make use of. We recommend measuring the accuracy using the area under precision recall curve to give a better understanding how good our model performs or not. But before that, you're going to downsample. Remember what I initially said about the amount column and the class column and the time column. It is not in the same. It is not normalized with the other columns, which we got from PCA, principal component analysis. So we want to scale it down to be on the same normalized to be normalized to the other columns. So the method we are going to use is the sklearn preprocessing model, which is the robust scaler. That's the one we're going to make use of for this. So here we are transforming and normalizing the amount column and the time column and making a separate column for that in our data set. So after when we finish working with that, we eventually have to drop the columns which we have gotten from. So we are going to drop the time column and the amounts column, and then make use of the scaled amounts column and then the scaled time column. So this is the normalized column. It has been normalized to this data set, to the amount and the time. So we can easily make use of it and make use of it in our training. So that's that. So how many of the columns? So we want to get our data set into the features and the targets, so we can use it for the training of our data set. So the data sets, so we are going to select the columns that are for the features and the columns that are for the target. So you just have only one column that is for the target, which is the class column. So we just run a simple logic. The columns that are not that are not equal to class is actually the features. The one that is equal to class column is equal to the target columns. So we have our X and Y. So let's see how our X is. This is our X column. So there is no class here. And if we run our Y, this is the column for the class, which contains whether it's fraudulent or not, as the case will be. So now we are going to see. So remember what we said, we want to downsample our data sets into, so we want to bring down the genuine transactions to be on the same level with the fraudulent transactions. So in this case, we are going to select the number of. So let me explain that one by one. So we have to select the number of our of the rows. How many of the rows do we have fraudulent transactions? How many of it at it? So the number of the fraudulent ones is, I think, around 492 or so. 492, right? So this number is what you're going to select randomly from the genuine transactions and then join it with the rows that are fraudulent to have 492 plus 490, which is 984, right? So here we have, so the one for the fraudulent. So we are converting it into an NumPy array. So this is the indices for the fraudulent transactions. Then for the normal transactions, the indices of the normal transactions. So now, after we have gotten the indices for the fraudulent and the transaction and the normal, we are now going to take from the normal transactions the number of equivalent fraudulent transactions. So if you have 492 fraudulent, you want to collect 492 of that bulk of how many data sets do we have for the genuine transactions. So we have card. This is the class column. Value counts. So we have 284,315 fraudulent genuine transactions, and we have 492. We want to select 492 randomly from these 284K genuine transactions, which is what we're trying to do here now. So you are doing it randomly. That's why we're using the np.random.choice. How many of it you are selecting it from the normal credit transactions? The number of it is from the fraudulent, and then we convert into an array. Then we join the normal and then the fraudulent, which is what we have here. So after that, we use the indices to be able to select it from the data set which we have, and we get our undersampled credit data. So this is it. So now if you look at this undersampled credit data, so we have the normal transactions. If you look at the tail now, it will give you the genuine transactions, the fraudulent transactions. So we have here now ones. So what it just did that it joined the one for the fraudulent beneath the one of the genuine transactions. So we have first of all zeros and then ones. If you count it now, you see that it's up to, they are equal. So we have 492 and 492. But we are not going to work with it in this way because it is not, it is too, I don't know the word I want to make use of now. It's too plastic. It doesn't look real or organic. So we want to make it to look a little bit real. So we have to shuffle the data set. We don't want to leave it like zeros and ones. We want to make it to see as if it's an organic transaction. So we don't know when the normal transaction is coming. We don't know when the further transaction is going to come in. So when we reshuffle it, then it is an okay for the training of the model. So yes, the length of the data set, you've already seen that it's 984 as the length of the undersample. So this is our undersample data. I just assigned it to this variable undersample data so that I can make use of it. Then, so we separate it as we did previously for the normal data sets. We have the X and the Y. So we have the target is the Y column, and then the features is the ones that are not of the target column. So we have our X and Y, our features and our targets. X is the feature columns, and then the Y is the target columns. So the Y is to be predicted. Now, after we finish training our models. So now it's no longer imbalanced now. It's no longer imbalanced. It is now, right. It's now, how do I put it? It is balanced. It's a balanced data set now. That's why you have 0.5 and 0.5. If you make use of the function which we did here in doing this, if you use it now in our new data set, you see that it is balanced. Or what we do is just edit it. So we are plotting undersample data. Undersample data. Let me call this one 1. So you see it is balanced. So the zeros and ones are actually balanced. So this data set is not yet, so we still have to reshuffle it, but it's almost close to the kind of data set we're going to make use of in our prediction, right? So we use this to reshuffle it. We're going to make use of this in the reshuffling of the data set. So using this function, sample and then fraction equals to 1, we reshuffle the data set. So it's now reshuffled. So if you look at it now, at least let us look at the class column. The first few class column up to 10 rows. Up to 10 rows. You see, it's reshuffled. It's no longer like zeros first and then 1. So you see 1, 1, 1, and then you see 0. You see 1, 1, 1. You see 0, 1, 1, 1. Let me reshuffle it again. It's reshuffled now. You see 0, 0, 1, 1, 0. So it's a little bit scattered. So we cannot make use of it in our training. We're going to use sklearn train test split to split data set to the training set and the test set. So that's it. The size of the test is 30%, while the training is 70%. Is good. So that's for the training and the validation of the data set. So this is for the training, then this is for the testing of the validation. It's total number 984 from the zeros and ones that we have already gotten before. So here we import all the modules we need. So we are going to make use of the machine learning module, logistic regression, and then the metric we are going to use is the ROC, area under curve. So that's that. Then I will explain the logistic regression function. Once I just put it here. So this is the logistic regression. So zeros and ones is the regression in zeros and ones. So we are going to use the solve of the lib linear, and then the penalty for wrong classification is L1. We're going to use L1 for that. And then so we train with the training of the X chain and then the Y chain. So these are the values for the Y chain, and then we ravel it to extend it. So what I mean by that is, so you have your Y chain. I've already run this. These are Y chain. So we want to get the values of our Y chain, which is this. But we are not going to work with it in this way it is. So you have to ravel it to extend it. So it's not be like in one columns. I think the shape now. 6 8 and 1. We just want to extend it. So there is no column in the data set. You just have to get the raw data set. So the values dot ravel. This is what the function does in the raveling of the data set to see how it has expanded it to be in this format. So I think the shape will be different from how it was. So 6 8, there is no longer column. It's just seeing it like a row. So that's what this thing does. And then the decision function for the scoring of data set. So once we do that, we predict on the test values. So we perform the same thing. No, we extend the test values like how we did it in the Y chain, but we are not going to ravel it because there's several columns in the test set. So we use that for the prediction. We feed the models with the X chain and the Y chain, and then we predict on the X test. And then after that, we will now use the metric for the model which we're going to make use of, which is ROC, area under curve. And then we get our value. So we run this. Our accuracy is very good. It actually worked very well. The metric for the area under curve is 98%, 0.98, tending almost to 1, which is actually good. But we're going to use another model also, and we are going to compare between the two of them, which one is better off. So we just use logistic regression. We're going to make use of random forest classifier. It's always good also in working with tabular data sets, tabular data set for regression problems. So this, which is what we do here. Almost the same thing we did in the previous one, but we're just using different models. And then we run it. Okay. 97. So it means that the logistic regression is much better off than random forest classifier. Okay. So now we're going to plot it on the graph to see on a visual representation of how the models are performing. So logistic regression, and then the random forest classifier. So this is the graph. This is the minimum. This is 50%, but it's more beyond that. These are the two models. It somehow seems that the logistic regression is 94 and the random forest is 93. So logistic regression is much better off than the random forest classifier. So this is basically a rundown of the training with of the prediction. So because the data set is for competition, and I don't think they released the one for the test data set. So you just make use of the model and upload it for the prediction on the test data set. But this is just like the first baseline of the training of data set on the prediction for credit card fraud detection. Then we can work on that model subsequently, whether we're going to use larger models and then to stack them and then to do more of the training of the data set. This is like just a rundown of credit card fraud detection, competition, and the technique we used. You remember what we used? We used because it's a highly imbalanced data set, we used the technique of downsampling. You can try out making use of the oversampling of the data set. You can try out the technique of the SMOTE, SMOTE, Depending on the one you can even use the 3 techniques or more of them and then join all of them together to get a better value for your model. So, but this is just a basic, simple um, technique on working with a highly imbalanced asset for credit card fraud detection. If you have any questions, or if you all have suggestions, or need more clarification on what we just did, now you can put it in the comment section concerning what we just did now. Bye for now, and see you another time again.